I'm just going to spend a few minutes going over a couple of overview slides to talk about our technology, and then I'll jump into a demo so you guys can see what the software looks like. PernixData FEP is a server-side acceleration software that basically installs inside of the ESX host as a VIB in the kernel space to transparently accelerate applications in your environment, both reads and writes. Our friends over at VMware tell us that roughly 70% of all support calls that they receive are ultimately traced back to some sort of performance issue on backing storage. So if you take a step back and look at who created our company, our software, Pujan Kumar, our CEO, is the former co-founder of Exadata for Oracle. He was also the former head of all VMware data products. Satyam Vagani, our CTO, you may not know him by name, but you'll know what he's done. He was the author for VMFS, the VMware file system, created VAI, and created vVols. On our engineering team, we also have a lot of core developers who wrote kernel-side software for both VMware, for vSphere itself, as well as for many storage systems. At a high level, what we've done is we've built a strategic infrastructure platform that decouples performance from capacity. So essentially what we're doing is creating an acceleration tier where we bring application data closer up to the ESX host itself, closest to the VMs. And we also buffer writes that are going back to the array on the back end. So what makes us different from others in this space? Well, accelerating writes for one, and doing it in a way where we're protecting the data for all of your enterprise applications. We do it in a way that's completely non-disruptive, that doesn't require any changes to your virtual machines or applications, that doesn't require any agents on the ESX hosts or inside of your virtual machines, I mean. We're also completely compatible with anything that's on the VMware HCL. So our hardware compatibility list is VMware's hardware compatibility list. We work with any server, any networking, any storage. What's really nice about that is we work with whatever you have today, but as you make decision changes over time for your infrastructure, we continue to work as long as you're compatible with VMware. The next innovation is what we're doing is aggregating flash and RAM from all of your ESX hosts, putting them basically into a pool and re-virtualizing them, making them accessible across all of the nodes in the cluster. We're a clustered solution, and this is important, right? Because what happens when you migrate a machine from one host to another? Typical read caching single host solutions will drop that cache, and now your application performance suffers while the VM has to go and get the data from the backing storage again. We don't. We keep track of the VM, which host it's running on, which host it moves to, and we allow it to actually access its data from the host that it came from. We also relocalize that data on access onto the new host. So always maintaining the performance for your applications. Clustering also allows us to provide fault-tolerant write acceleration. This is the secret sauce in the software. This is why people use our software for enterprise applications as opposed to only for scenarios such as VDI. Every time a write comes in from an application, we replicate it to up to 2 peers within the cluster, and then we acknowledge back to the virtual machine and the application can proceed. What that does is it gives your applications that performance of server side, right? But your VMs, your data continue to live on the backing array. You don't make any changes to your VMs or to your applications. From a failure handling perspective, let's say you're using a flash device, we're completely transparent to the back end and to the front end. So what that means is if a flash device fails, your VMs don't even know that anything changed. The applications don't realize it. We didn't present any new data stores. Your VMs aren't living on any different storage, right? The VM continues to run, it just no longer has the same performance. Now to fix that, you can simply reassign that VM to, say, a memory tier, allocate a bit of RAM for acceleration instead, or simply vMotion the VM to a different host that has working flash or RAM. And that application will be accelerated all over again. A topic that's come up lately has been in-memory computing. I don't know if anybody here is looking at that. You know, products such as SAP HANA, if you're using buffer caching inside of Oracle or SQL Server 2014. One of the really interesting things that we do is because we leverage RAM for accelerating both reads and writes, you get the benefit of in-memory computing at the infrastructure layer. So you're no longer relegated to using in-memory for applications that were written for in-memory. And even applications such as SAP HANA, for example, will use memory for read caching only. They can't commit the write until it's been committed to non-volatile media, right? So what happens? Typically, the recommendation might be, for example, to leverage a local flash device, but then now you need to migrate your VM up to the ESX host, losing VM mobility. Does that make sense? With PernixData, because we're replicating the writes between peers, as that write comes in, we make up to 2 copies of the data and acknowledge it back to the application. But that data persists and migrates down to the storage on the back end, so to your non-volatile capacity layer, without taking the performance hit and without losing the mobility of that application. Why do we think this is the right time to do this? Well, if you take a look at the processors coming out by our good friends over at Intel, we have sockets coming out now that can support 1.5 terabytes of RAM per socket, right? The price point today may not be where we're putting it in all of the boxes yet, but it's very common for us to see customers already putting 768 gigs of RAM in a single host, for example. Because we pull that across the cluster, that's a lot of memory to work with. When using memory, we also implement a feature called DFTMZ, which is memory compression. So we will compress data in memory as well to try to basically extend that investment of a very limited resource. And as I mentioned earlier, this is in-memory computing at an infrastructure layer, right? Why should you have to wait for an application and license an application that's written specifically for memory when, because of where we sit in the stack, that big red bottom of the triangle there, you can have in-memory SQL today, in-memory Oracle today for both reads and writes without making any changes. You don't have to mess with buffer caches. You don't have to mess with having SQL Server VMs, database VMs that have 0.5 terabyte of memory allocated to them, right? Taking away from memory for the other applications in that cluster. Put it down on the infrastructure layer and allow it to be shared across the board. But now you can have in-memory Exchange, in-memory SharePoint, in-memory that application that was written 20 years ago. Put it in memory and run it that way. As we're running out of time here, I'm going to go ahead and switch to a demo real quick so you can see what this looks like. Can you see that okay? I know it's a little bit small because of the resolution, but it's full screen. So here you see an example of our UI. We integrate directly into the vSphere web client. So this is the UI that you're already using every day to manage the virtual environment. In this example here, you can see we have 3 FEP clusters created. You can actually tier different acceleration media. So that top tier, DFTM, is that memory tier where we're leveraging RAM for acceleration. We've got a PCIe flash cluster, which is using flash cards for acceleration and SSD. Now you can take those and allocate VMs to each one to gain different performance characteristics, for example, or to meet different SLAs. Maybe you only want your database VMs using in-memory. Maybe you only want your infrastructure VMs using SSD. Maybe you want your old OLTP applications using PCIe flash, right? Now for each one of those, we can take a look at a little bit more information and see here, for example, on the PCIe flash cluster, but you can see a summary of this particular cluster. So we'll show you some interesting information such as how many hosts are in the cluster, how many of them have acceleration resources. You're not limited to only 1 per host. You can accelerate using multiple acceleration resources per host. You could put 2 cards, 3 cards, same with SSD. What's really interesting about this is how much data for your applications you can bring up to the ESX host. When using memory, we allow you to allocate up to 1 terabyte of RAM per host. On a 32-node cluster, that's 32 terabytes of RAM for acceleration, and we compress data there too. On the flash layer, vendors such as HGST, for example, are coming out with flash devices that are 6.4 terabytes for a single card. Now imagine that times 32 across your cluster. A lot of data coming up to that application layer. We'll show you some performance statistics on the right side here. In the bottom right-hand corner, we have this historical view, or what I like to call the hero card. Right? We can see that we created this cluster 6 months ago. And since that time, we've actually offloaded over 238 billion I/O from the backing storage. This is I/O that that backing array did not have to do because of the read caching functionality of the software. We also saved, or we offloaded, over 1 petabyte of data from being transmitted over that backing storage network. Right? So if you're using 4 gig fiber channel, 8 gigabit, 10 gig iSCSI, even 1 gig iSCSI, this is data that never had to traverse that storage network. And we accelerated over 49 billion writes. Writes always make it to the backing storage, but we acknowledge them on the server tier after they have been protected. FVP network savings here, you see a 0 because we're on a 10 gigabit network. If you're using 1 gigabit networking, like 1 gig iSCSI connections to your backing storage, we have a feature called adaptive network compression. What that does is we will automatically compress data for blocks that are 16 kilobytes or larger before we send them to a peer for protection. There is a bit of a trade-off. It's about 1 to 2% CPU to do that. But the flip side is, because we see compression of up to 7x, real-world customers will see that 1 gig network behave a little bit more like a 3 to 4 gig network, extending the life of what they already have, right? Maybe you have plans to upgrade, you just can't do it yet. Maybe you bought the gear, you just can't implement it yet. When you move to 10 gig, you'll get all the benefits of 10 gig. From a performance perspective, we show some pretty interesting metrics too. So as you can see here, we're in the storage path, so we're able to report on front-end and back-end latency. So very rich graphics about what's going on from a performance perspective. This purple line here, you can see is the data store line. If I highlight this point, you can see that when our backing storage was delivering about 15 milliseconds worth of performance, the performance to the VM, what the actual VM was seeing, was only 990 microseconds. So sub-millisecond latency to the virtual machine. If I expand this, I can even give you a more detailed view of what's happening here and break out the read and write latency for the local acceleration media, for the network acceleration media. Remember, network acceleration write is after a VM migrates from one host to another, we allow it to access the cache that was already pulled up on the server tier from the other host, as opposed to going back to the backing storage. Network acceleration write is protecting the writes between the peers. Now, when we take a look at some of these metrics again, you can see we have an even more granular view of what's going on. So back on the same data point where we had 15 milliseconds on the back end, we can see that this was 100% write, that there were writes that were protected between peers, and that we were leveraging roughly a third to half of a millisecond of latency off the local flash device. We do the same thing for IOPS, throughput, hit rate, and eviction rate. So IOPS and throughput are interesting, right? IOPS is something that a lot of people like to talk about. We happen to believe that latency is a lot more important for application performance. But we can do the IOPS and also report on where those IOPS are coming from. So on this data point, you can see we had over 14,700 IOPS. These are just 2 VMs on a couple of nested ESX hosts. But you can see that 13,000 of them came off the local flash device for reads, while at that time, 0 was coming from the back-end storage. So at this particular point in time, we had a 100% hit rate for this particular virtual machine. You can see that the VM was also issuing writes at the time. They were protected on the peer and made it to the backing storage. Now, this is not some sort of a scheduled task. We don't like commit the data down every 5 minutes, every 10 minutes, every 15 minutes. This data is destaged asynchronously, but as soon as possible. So let's say that your VM is seeing 1 millisecond of latency, but the array is doing 15 milliseconds. Well, roughly 15 milliseconds later or so, that data will make it to the backing storage. But if the array happens to be busy, maybe your storage processors are busy doing something else, they can't, latency is going up, maybe the disk is busy, maybe your network bandwidth is constrained, maybe the queue depth on your HBA adapters is exhausted and there's not even a problem elsewhere, you're just not leaving the host fast enough. That increased latency will not be visible to the virtual machines because that data is already on the hot tier, it's on that acceleration tier, on the host, it never hits the HBA, and any writes are acknowledged on the server tier as well. Make sense? Throughput is sometimes an interesting metric. Just dividing the IOPS into the throughput will give you the average block size for your applications at any particular point in time. The question that often comes up is, well, how do I know how well that acceleration tier is working? And that's this hit rate and eviction rate graph, right? Right now, we're seeing what we like to see, which is most of the time we're in the 99, 100% hit rate in a production environment with a lot of VMs, a lot of different applications with many different performance profiles. We tend to see that hover between 80 and 100%. But if you saw that hit rate be consistently low, that would be an indication to go take a look at something. Now, keep in mind, hit rate is a read cache hit. You can't have a hit rate on writes. Writes are always accelerated anyway, but a cache hit rate is for reads. Another question that often comes up is, well, how do I know when I don't have enough RAM for acceleration, don't have enough flash? Well, partly it's going to be a reduced hit rate, but partly it's going to be reflected by this orange line at the bottom here, this eviction rate. You can see here it's at 1%. And what that means is that we're just kind of lazily evicting the coldest data that we have on our tier to make room for new hot data coming in. Notice that we manage the space automatically. You configure acceleration policies on a per virtual machine or per data store basis. You can say, I want every VM on a data store to be accelerated for read caching only. Maybe I want other data stores to be my write back accelerated data stores. And you can do it on a per virtual machine basis as well. Everything in the UI can also be driven via PowerShell. So if you have workflows where maybe your customers, your business units are requesting virtual machines through some sort of automated interface, you can code that in, right? You might be using Manage Engine, you might be using VCO, maybe VCAC. You can incorporate the selection of acceleration policies in those workflows as well. From a usage perspective, we'll also show you how well flash devices are being used. In this particular subcluster, we have 2 VMs running on this tier. So you can see how much flash they're using for each VM and whether any of it is coming over the network. Is there any data remote that's being accessed? That's that network acceleration usage number. So in this case, the VMs were migrated at some point, and they still have some data on the other host. As they need it, we'll go get it and relocalize it. For each VM, we'll also show you which flash or memory devices are being used to accelerate them. The reason why this might matter is because let's say you have a, latency is going up on a particular VM or in a particular subset of VMs. You can see which flash device they're on, and maybe that flash device is having a performance issue. Maybe it's a failing SSD. You can catch that early and replace it. Because there is no data at rest on our tier, doing that kind of swap is live. All the data resides on the array on the back end. Make sense? I just mentioned you could take a look at the performance for the resources Here, from a usage example, I'm doing the reverse of what we did earlier, selecting an acceleration media, and you can see which VMs are leveraging it. But if we go back to performance, we also show you the performance for every individual device that you're using for acceleration, whether it be memory or flash. We have some customers who love this because it helps them evaluate what type of flash devices to use. Right? Let's say you've got a selection of 5, 6 different models and vendors of flash devices. Well, it doesn't help a lot to have to use a unique interface from each vendor to look at what the performance stats are. Here you can use a central tool and compare them all at the same time and side by side. That's pretty much the UI in a nutshell. What we do is pretty straightforward. One thing I did want to call out is that everything I'm showing you in this demo, you can actually take a look at it yourself. We have a self-demo button on our website. It'll create temporary credentials that are good for an hour, so you can come in and poke around the same UI I just showed you. We also have a number of certifications, a number of white papers, and also solution sheets. So based on your array vendor, your server vendor, you may want to know, what does this look like in practice? Right? We've got documents for that as well.